In this module, we're going to look at strategy. I think you'll agree, whether you're a coach or an athlete or a fan, that strategy is crucial to any sport or any situation where we have conflict or confrontation. And we're going to see how probability and expected value can help us make better decisions on strategy. For example, some situations might be, should a team foul or not in order to keep their lead at the end of a basketball game? How often should a football team run the ball and how often should they pass it? And how often should a soccer goalie dive to the left and how often should they dive to the right? So these are all questions about strategy, and we're going to try to see if there's an optimal strategy for some of these problems. One of our main tools, and a very useful tool in calculating probabilities and making decisions, is a tree diagram. And a tree diagram is very useful for choosing a strategy in an alternating move game, such as perhaps chess, although that's a very large tree diagram to work with. And it's also especially useful for calculating probabilities in a number of situations. Situations where there are sequential steps in an experiment, or when we carry out repeated trials of the same experiment, or if there are a number of stages of classification in objects sampled. Okay, let's look at a simple example. Suppose we have an experiment. We have an urn containing 6 red and 4 blue marbles. And I perform a two-step experiment. I first draw a marble from the urn, and I leave it one side, and then without replacing it, I draw a second marble from the urn. And let's think about the problem. What's the probability that both marbles are red? Well, because there are two steps in the experiment, a tree diagram is ideal for solving this problem. So we can draw a diagram to represent the possible outcomes of the experiment, and we're going to label it with the appropriate conditional probabilities. Now, on the next slide, we're going to abbreviate the first row to first and the second row to second, and we see the outcomes here represented on this diagram. So when we draw the first marble, we can get either a red or a blue, and then on the next row, we can either get a red or a blue, or a red or a blue here. Now we'd like to put some probabilities on each branch of the tree diagram. Well, at this point, we're going to fill in the probabilities on the tree diagram we've just drawn. And notice these are going to be conditional probabilities, the probabilities we studied in the previous module. And here we're going to have a probability. We're going to place the probability of getting a red on the first row on this branch, and the probability of getting a blue on the first row on this branch. And on the next branch, the probability that we get a red is going to depend on what came with the first row. So this is going to be the probability of a red on the second row, given that we got a red on the first row. And here we're going to put the probability that we got a red on the second row, given that we got a blue on the first row. Okay, let's have a go at filling in these probabilities. So we have our experiment where we have 6 red and 4 blue marbles in the urn. So on the first step, we draw one marble. Let's suppose it's red. So let's suppose we get a red on the first. Okay, well, it's easy enough to fill in the probability that that's going to happen. We have 6 red and 4 blue, so the probability we're going to get a red on the first is 6 out of 10. that goes right there on that branch of the diagram. Now, I don't put that red marble back in, so the chemistry of what's in the urn changes. So that marble doesn't go back in the urn, it goes away, and now I have 5 red and 4 blue marbles in the urn. So now, on the second draw, I take a marble out, and the probability that that's going to be red is going to be 5/9. So the chemistry in the urn has changed. There are now only 9 marbles, 5 of which are red. So this conditional probability, the probability that I get a red on the second, given that I got a red on the first, is 5/9. Okay? And then, of course, the probability that I get a blue here on the second draw, well, there are 4 blues out of 9 marbles, so that's 4 out of 9. Now, if I got a blue in the first draw, these probabilities would be different. The chemistry in the urn would be a little different after the first draw. So I start with 6 red and 4 blue, and suppose I drew a blue marble on the first draw. Well, the probability I'm going to get a blue marble in the first draw, there are 4 blues out of 10 marbles, is 4 out of 10. And now, the chemistry in the urn, that blue marble doesn't go back in. So now I have 6 red and 3 blue in there. So when I draw marbles from the urn again, on the second draw, the probability of a red, I have 6 red out of 9 marbles, so the probability of a red is 6 out of 9. And I have 3 blue out of 9 marbles, so the probability of a blue is 3 out of 9. Sorry, that goes up there just a little bit. So now we filled in the probabilities on our tree diagram, and you'll notice that every path on this tree diagram represents an outcome for our experiment. So we might get a red on the first and a red on the second, or a red on the first and a blue on the second, or a blue on the first and a red on the second, or a blue on the first and a blue on the second. And this is all that can happen. We can only get those 4 outcomes for our experiment, and now we'd like to use these probabilities to calculate the probability distribution in a table for our experiment.